This first one, I think we had good success. And remember that that notation means this, which is this is a better way to write it. So you at least got to imagine that this way. So cosine squared x is cosine x squared. This is a preferred way. And I think that most of us got this, that it's undoing the chain rule, right? Sine is the derivative of cosine. So this is undoing chain. This one also had very, very high success. We see 2 powers of x times cosine x, so this is going to be undoing product. And it's going to require that twice, once nested inside another time, right? For every power you have here, you have to work through it too. So we had good success on those. Low success on this one. Remember, inverse trig functions. Inverse trig functions is a common form of undoing product. So remember, we did inverse cosine in class, and we listed this as one of the common forms for undoing the product rule. So inverse sine, inverse cosine, inverse tangent, or arc, those are all done by undoing the product rule. Okay, so it's not a trig identity. None of the trig identities involve the inverse trig functions. The inverse trig functions are undoing product rule. Okay, this was very high success again, undoing chain. Okay, so this one, rewrite it. So lots of you on this one said undoing chain rule. What's wrong with that? What would you need for undoing chain rule on this one?
Cosine on the outside.
Yeah, you'd have to have a cosine here, right? You have to have the derivative of the inside along with it. But it's not there. You don't have that. So this is going to be a trig identity. It's not going to be undoing the product rule. And it's not undoing chain, so this is a trig identity. As is this. We talked about this last time. We have different arguments, right? We did an example almost like this last time. You have a different argument, 2x versus x. So again, you're going to start with a trig identity on that cosine 2x. All right, any questions on these?
Yes, if you could you just explain again why the last one was a trig identity?
What would you think it might be instead?
Well, I thought that it was the chain. I'm sorry, that was my computer. I thought that was the chain rule because
Yeah,
you
but
have the derivative.
chain rule, no, chain rule would be this would have to be the derivative of the inside of this one.
Oh, right.
So
Yes.
that doesn't work, right?
Yes.
So
Yes.
the derivative of that is 2.
Yeah.
So if it was cosine of cosine x, so cosine of cosine x, that would then, with the sine x, then that would be right.
Right, of course.
Yeah.
Okay, thanks.
Yep, sure. Other questions on these?
Yeah, I thought the last one was product rule, but I guess that's completely wrong because that doesn't make sense.
It's possible, but it's not one of the common forms, and it would not be easy. But this is really similar to the example we did in class last time, where one was the 2x argument, the other was the x argument, and we have identities for cosine 2x.
Yes, that makes sense. Thank you.
Other questions? Okay, yeah, so like we've talked about before, as we have gained more and more of these different techniques, then the identification becomes a new issue, right? It's not going to tell you on the test, do it by this technique. You have to look at it and say, oh, this is what applies, or this technique. So that's why we're starting to practice that. And you'll get, and then you should start studying for the exam. You have lots of practice of that. Okay, so we have one more trig, the one we started last time, which we need to finish. And so let's look at that one. Sorry, that's a little blurry. I'll rewrite it here. Okay, so we had this one. So let's just recap what we're going for here, right? So we said with these trig identities, you're either using identities in algebra to make it simpler, so it's just really kind of a straightforward antiderivative, or we're trying to stage or set it up for undoing the chain rule. So what would undoing the chain, let's look at some examples of what undoing the chain rule would look like. So we had this one of sine x cubed on the quiz, but we would also need what for it to be undoing the chain rule?
Cosine.
Cosine x. Why? Because cosine is the derivative of sine. And that's the result of a chain rule right there. Okay, what about if it was some power of secant? So if I could have any power of secant, what would I need in addition so that, or also multiplied, so that I could do undoing the chain rule?
Tangent.
Tangent?
Yeah.
Secant
times
tangent. Right? Because secant tangent is the derivative of secant. Okay? Another one, let's say if I had, I could have any power of tangent x as long as I also had what?
Secant squared x.
Secant squared x. So this is the kind of thing we're staging for. We're going to rearrange, reformat our rate function, our rate of change function, so that it looks like this. It looks like a trig function to any power times the derivative of that trig function. And then we've got undoing the chain rule, because we just raise the power on our trig function. That'll collapse back in. And we'll just be doing undoing the chain rule. So I think, so we started off on this one going for this. So we want, if we can gather all powers of trig, any powers of tangent that we want, with a secant squared, we'll have it. So we started by pulling off a secant squared. And I made a pretty bad error last time, if you noticed. So what's going to be left? When I pull out secant squared, I'm going to still have another secant squared. I think I put a plus here. It should be times. Plus is coming, but not yet. Okay, so understand what we're doing. I'm seeing lots of tangents and secants, so I'm thinking, what if I could get it to look like this? I could get it to be any power of tangent times secant squared, then I'd have undoing the chain rule. So I got my secant squared. So now I got to get this to be all powers of tangent. So I got to work on this. How can I get that to be powers of tangent? Do we have an identity that I can get from this to tangent?
Yeah, secant squared equals tangent squared plus 1.
Okay, cool. Yeah, there's the Pythagorean identity. So you said what? Tangent squared plus 1?
Yeah, I think so.
So that's secant squared. And that would be times tangent to the 7th. And now look, I have my tangent to the 7th. And everything's tangent here, so this can distribute now. So that secant squared became a sum. So now I can distribute, I got tangent to the 7th times tangent squared, and tangent to the 7th times 1. And so then that will be what? Tangent to the 9th plus tangent to the 7th. Okay, so stop me if I lost you along the way here. Everyone following what I've done so far? Here's my goal. Get it to look like this. Secant squared times powers of tangent. So I pulled off a secant squared. Then I have what's left. I want to get all in terms of tangent. So I change the secant squared using the identity to tangent squared plus 1. Then I distributed my tangent to the 7th, and here I am. And so now I actually have 2 undoing the chain rule, right? So I have the secant squared paired up with tangent to the 9th, and I have the secant squared paired up with tangent to the 7th, both of which are undoing the chain rule. And then I have another layer of undoing the chain rule with the 3. Okay, so we're gonna have to take care of the 3 too. All right, so I got 7. So we can just pull the 7 all the way out here in front and just forget about it. So it's like pull this up, put the 7 in front if we want, and then do 7 times the antiderivative. Okay, so what's the antiderivative of secant squared times tangent to the 9th? Secant squared times tangent to the 9th.
Tangent to the 10th.
Tangent to the 10th. And now how I got a little mess to clean up here. What I'm going to need in front of here to take care of this.
1 over 30.
I need a 1/10 and also
1/3.
a 1/3. 1/10 for my power of 10. A 1/3 for my factor of 3 that will be like the second layer of chain rule, right? And then similarly, we're going to have the same thing. And this will be tangent to the eighth. And I'll have a 1/8. And also the 1/3 again. Okay, please ask if I lost you.
Where did the secant square of 3x go?
It's undoing the chain rule, right? This is the derivative of tangent. So just like all our undoing the chain rule problems, the f prime goes away, right? Because it collapses back in. We're doing g prime f times f prime, and then we're collapsing that to g of f. Like all the undoing the chain rule problems you've done before. Chain rule means this pops out. Undoing the chain rule means it goes away.
Oh, I see. Okay, thank you.
Yep.
So the secant squared was the f prime.
Right, yeah, that's the whole point, that we're going to get any powers of tangent that we want with a secant squared. There's our f prime. And then when you do undoing the chain rule, just like we've done it the last week, the f prime goes away.
And it's just, you're saying that the g prime would be tangent 3x to the 9th? That would be
To the 9th. The g prime is to the 9th power, and the f is tangent, right? So this is tangent to the 9th. So the 9th power is the g prime, and the interior is the f, is the tangent, and the derivative is secant squared.
Okay. And then what about the tangent to the 7th? Or we haven't gotten there yet?
Yeah, we did it right here. So it's the same thing again. So now you have secant squared times tangent to the 7th. It's the same thing again.
Yeah, I understand that. Okay, thanks.
Sure. Okay, does it make sense?
I'm sorry, I'm kind of confused on the 1/3.
Right, so there's like another little chain rule in here, because when you do the derivative of, tangent of 3x, it'll be secant squared of 3x times 3 by another chain rule. Does that make sense?
Yeah, thank you.
Yeah. Other questions? Okay, so you have practice with that. Is that due at midnight tonight? Is the trig identities? No, that's trig identities is due Wednesday, I think. Your the partial fractions? Is it due at 5 or midnight tonight?
Midnight.
Midnight. Okay, so partial fractions is due at midnight tonight. I think trig identities is then also due at midnight on Wednesday. So you got office hours and during the day Wednesday to get your questions answered on that. And we have one more technique before the exam on Friday. So are we ready to move on to that one? Any more questions? All right, here we go. So let's look at a new problem here. This one. Okay. E to the 2x over e to the 2x plus 3 e to the x plus 2. So first question we always ask is it undoing the chain rule? Is it undoing the chain rule? Okay, so we got this thing to the -1. Is e to the 2x the derivative, or essentially the derivative of this denominator here?
No.
No, because you'd have two terms. Like this is good. E to the 2x is e to the 2x. But this would be missing, right? We need another term that's the derivative of this one. So it's not undoing the chain rule. Undoing the product rule, looks a little scary. It's definitely not one of the common forms of undoing the product rule. It's not trig. So if we look at this, what does this kind of look like? We've got, what, squared, and then it's the first. What does this kind of look like?
A polynomial?
Yeah, right, exactly. It's kind of like a polynomial, but then it's got all these e's in it, right? It's got all these e's in it. And so what we can do to make it look like a polynomial is we can say, let's change the variable here. to say u. And let's let u be e to the x. And when we do that, we're gonna then if we change it into u, then those exponential functions will go away, and we'll have a rational function. It'll be like a polynomial over a polynomial. Okay, so if u is e to the x, then what is e to the 2x? Would be what?
U squared.
That'd be u squared. So now we know what e to the 2x is. We know what e to the x is. Last thing we need is dx. Okay, so what we can do is we can take the rate of change. What is the rate of change of e to the x?
E to the x.
It's e to the x. Okay, so that means that given any change in x, looking at this function here, the corresponding change in u is e to the x times that change in x. Right? So if e to the x is the rate of change, then given any change in x, multiply the rate. So this is all familiar, what? dy equals mdx, right? dy equals mdx. So then what does that mean dx is? Because that's what we really need to know is dx. So dx equals du over e to the x. But what's e to the x?
U.
U. So dx is du over u, if I just follow the math here. So now we've got everything we need to rewrite this integral in terms of u. And so it will be, we know e to the 2x is our u squared. Three e to the x is
3u.
3u plus 2. And then dx was du over u. So now this u that we happened to get when we did the dx part will join up with the rest of the rate function. Okay, so now this u becomes part of this. So now here's my rate function in terms of u. And what can I do right off the bat here? Make things easier?
Cancel your.
Yeah, because I have one u. Now this is not, in these problems, this is not always going to happen, but it's happened in this problem, and so we do the math, right? So u squared over u is but if this turned out to be u squared, then they would both go away and this would be a 1. If there's no u down here, then this stays u squared over this, okay? But in this particular problem, we had a u in the denominator and we have u squared in the numerator, so that makes u in the numerator. What do we got now?
You can factor the denominator to u plus 2 times u plus 1.
Yep, we are a rational function with the degree of the numerator less than the degree of the denominator. The denominator factors to u plus 2, u plus 1. And so we can use partial fractions now in terms of u. So I'm going to go fast just for time's sake. This is kind of the most basic partial fractions problem that we'll see. I'm going to go a little bit fast. So it's going to be, we're going to have a over u plus 2 plus b over u plus 1. Our common denominator will simply be the product of these, and so to get the common denominator in the first fraction, I'll have a times u plus 1 over u plus 1. To get the common denominator in the second fraction, it'll be u plus 2. And what does all that have to equal?
U.
The original numerator, right? So u plus 0. So then I got AU, or so the coefficients of u would be a and b, so a plus b is going to equal 1, and a plus 2b is going to equal 0. Right, so a plus b equals 1, and then a plus 2b equals 0. So we can just do a quick elimination here. Subtract and I get negative b equals 1, so b is negative 1, and that makes a 2. In order for a plus b to be 1. And so then this becomes a is 2 over u plus 2 plus negative 1 over u plus 1. Okay, how am I doing? Have I made an error? I don't think I've made an error, but if you see an error, please speak up as soon as you think I have. And then this is a pretty basic here, 2 times natural log of u plus 2 plus negative natural log of u plus 1. Are we done?
No, you have to resubstitute.
Yeah, so our problem was given in terms of x. This was the rate function in terms of x, and we want the closed form of the net accumulation function in terms of x, and so we just simply go back to our u is e to the x, and we apply that. So we got 2 natural log of e to the x plus 2 minus natural log of e to the x plus 1, and then we can add our plus c in there.
How did you manage to get negative 1 for b?
I subtracted the equation, so I got minus b equals 1. So b is 9. I subtracted the second equation from the first.
Oh, I see, okay.
Okay. Other questions? I went fast, so I'll take time for algebra questions here.
I have a question about if the limits of integration were defined.
Yeah.
Then would you have plugged in the limits of integration into the U-substitution and then changed it that way? So like if it was 0 and 1,
Yeah.
you would have plugged in e to the 0 and e to the 1.
It's a great question. In fact, that's just what I was about to talk about.
Oh, cool.
Say this was, no, it's a great question. So say this was like 8. So if the limits were, say, 8 to 11. Okay, so we're going to start accumulating at 8, and we want to know the net accumulation from 8 to 11 if the rate of change was this. So you have two options. We can take it all the way to the end and do what we did, and then apply the fundamental theorem with 8 and 11. Right? That makes sense, right? So it's kind of, when you move it to u, just scrap the limits and work the whole thing, get your closed form in terms of x, and then you would apply fundamental theorem. Plug in 11, plug in 8, subtract, right? Or you could make new limits on this. What would the new limits be on the u? So what would the lower limit be? This is x equals 8. So what would u be? When x equals 8.
Is it e to the 8th?
E to the 8th, right? I don't know if you said u or e, but it'd be e to the 8th, right? So if x is 8, then u is e to the 8th. And your upper limit would be e to the 11th. So now, since we have like a net actual final net amount of accumulation, and we don't care about the function anymore, then we could just apply that here. We could come to this step. We wouldn't have to change it back to x, and we could use the limits in terms of u with this form, right? We could plug in e to the 11th and e to the 8th and subtract. So either way, so you can either change the limits into your new variable and then apply that to the antiderivative in terms of the new variable, or you can take your function all the way back to the original variable and use the original limits.
Okay, thank you.
Yeah.
I have an algebra question for you.
Yeah, sure.
So when we do partial fraction decomposition, is there a reason why, like after we get to the part that says a times u plus 1 plus b times u plus 2, that we can't just substitute, or that we shouldn't just substitute like negative 2 in for u to get rid of the b and then...
Yeah, you can do that. But I like this because it refreshes your ability to solve systems of equations. So that's why I teach it that way.
All right, great, thanks.
Yeah, but you can do that.
What if we had a case where the u at the bottom, so it's du over u, didn't cancel? What would we do then?
Yeah, just the u becomes part of the, if there, if there's nothing up here, that's like 1, then the
Yeah.
u just multiplies times the denominator.
Oh, it just multiplies. Okay.
It's part
got
of the rate. It just be whatever you get with the du becomes part of your rate function, and then if you can simplify, you simplify. If you can't, you don't. But it becomes part of the whole rate function.
So it would be like u to the third plus 3u squared.
Yeah, you would, but yeah, we want to factor it eventually. Yeah, so if this was 1 up here, say this was 1, then we would have u times u plus 2 times u plus 1.
Right. Okay, awesome.
Yep. Yeah, that's important. This isn't going to be, every problem isn't going to be just like this, where you get a u and you cancel it out with the top. That's, you have to just do the math. And this just multiplies. This is just really multiplying into the denominator here. Other questions? All right, let's look at another example. So this is the idea of a change of variable, or also called U-substitution. And so many of you may have learned U-substitution, and you've learned it to do problems like this, but then also to do problems that we're doing by undoing the chain rule. And so the reason I recommend the undoing the chain rule is because once you get good at that, it's a lot faster and more efficient than working through all this, changing it in, doing all this setup work, changing the integral into u, doing the antiderivative, changing it back to e to the x. It takes a lot more work. When if you recognize undoing the chain rule, you get better at it, and you can just start writing down the antiderivatives almost in one step. So that's why I'm encouraging that. But then there are these problems like this that aren't undoing the chain rule, where U-substitution is kind of a must, and that's what we're going to emphasize. Okay. Next one. So here's one. So the first question we always ask is it undoing the chain rule? Is it undoing the chain rule?
No.
No, and we say, okay, what small change could we make to this so that it would be undoing the chain rule? And I want to keep both factors. I want to keep something, a y here, and keep this. What small change then would make it undoing the chain rule?
Square the y on the inside of the cube root.
Yes, right. So we got y, like y to the first. That means this interior function would have to be like y squared. Now we would have undoing the chain rule, because y is essentially the derivative of the interior. But that's not our problem. We have a different problem. We have this one. And so what's really the obstacle here in doing this? And so you might think that maybe undoing the product rule would work for this, and I think it does actually. But it's a little bit harder than using a substitution. Okay, so this isn't one of our common forms for undoing product, but I think it works if you do things correctly. But like I said, making a substitution, changing variables, is actually easier. So what would what's tripping us up here? A cube root of a sum or a product is very, very confining, very locking. You can't do anything with that when you have a difference or a sum under a radical, right? That's very locked. So what should we make u?
Y minus 8.
Yeah, if we make it y minus 8, then we'll just have like a cube, like u to the 1/3. That gives us a lot more freedom, right? We've gotten rid of the sum or difference under the radical, so that could potentially be really helpful. Okay, and so we need to know what y, so we got y minus 8 is u. We need to know what y is. What would y be in that case then? It means that y is what?
U plus 8.
U plus 8, just do the math, right? And then we need dy, right? So we need dy, so we can come over here and we can say, what's the rate of change of u plus 8? What's the rate of change? 1, right? The rate of change of that is 1, meaning that given any change in u, the change in y is 1 times the change in u. It's our friend, right? dy equals m dx. So that tells us what...
Sorry, can you just go back again? Why is it 1? Why is
the rate of change of this, the rate of change of u to the 1 u to the first?
Yeah, why is it 1 again?
The derivative?
Oh, it's just the derivative of u.
Rate of change is derivative. Yeah, to get the rate of change, you take the derivative.
Awesome.
Okay, and so then we got our y. That's our u plus 8. And we got our y minus 8, so it's going to be cube root of u. And we got our dy, which in this case is just du. So did it help? So we got u plus 8 times the cube root of u times du. Did it help?
I feel like we're back in a similar spot.
Oh yeah. So is it the same kind of stuck place we are here, or is there something now we can do?
We could multiply the cube root into the u plus 8.
Yeah. So look. So now I just have u to the 1/3 here, and it's times u plus 8. Well, we can distribute, right? I can just distribute u to the 1/3. So I'm going to get u to the 4/3 plus 8 u to the 1/3 du. Is this doable?
Yeah.
Very doable now. Power rule. Not even undoing chain, just power rule. So we got u to the 7/3, right? Raised power times 3/7 plus 8 times u to the 4/3 times 3/4. And we'll have a simplification there. That'll be 6. 8 divided by 4 is 2 times 3 is 6. And then can I do that and put my y minus 8 back in at the same time? So 3/7 u is y minus 8 plus, this is all 6 times y minus 8 to the